Hello, everyone, and thank you for joining us for the Sensors Driving You Mad webinar presented by my friend and mentor, Leiv Rieger. Leiv is the CEO of InCTRL Solutions and specializes in instrumentation, monitoring, modeling, and control of water resource recovery facilities. A focus of his work is to develop new tools for data quality evaluation to more effectively optimize treatment processes. Leiv has been a leader in our field for quite some time. He was the founding chair of the International Water Association Task Group on Good Modeling Practice and was the past chair of the Water Environment Federation Modeling Expert Group of the Americas. Really happy to be a part of this webinar, and Leiv, I'll hand it over to you.
Thanks, Alex. Let's share my screen. Yeah, thanks for the introduction. Our second webinar is about selecting and operating online sensors, and well, I tried to put some slides together, and I actually ended up with material for probably a couple of days. So I had to reduce to stay within whatever 30-40 minutes. So what I try to do is focus on my personal view on online sensors, and I try to highlight a couple of things you may not be fully aware of. Yeah? So an outline of that webinar, I would like to take about 2 minutes to go over InCTRL's expertise and offering. So that is focused actually on instrumentation and data quality. And then going into the actual webinar, I start with sensor selection and then further talk about sensor operation. And I split that into commissioning, maintenance, and quality control. And of course, there will be a couple take-home messages. The question and answer section, I will hand back to Alex. He has prepared a couple new surveys or additional surveys to make that more interactive and get a better feedback on what you are doing actually. So let's look at what InCTRL is doing. So our focus is more on the water quality sensors, and we mainly work in wastewater treatment, also a bit in collection, and then waste management, so that is biogas plants. So we provide expert advice, we do consulting projects for clients and also give training courses. So that could, for example, be that we help you in selecting the right instruments. We can help you setting up and designing test campaigns. We will help you or guide you through the evaluation process so that you have proper recommendations. We also provide calibration support, so that is very hands-on to make sure that your sensors and analyzers properly work. We also develop maintenance plans, so we can support you in putting that together, or we can also develop the full plan and deliver that as a report or even packaged in software. We also do a lot of data quality evaluations and reconciliation, so we can help you with your data. We also, of course, work with data, so we are not just collecting it. So we are setting up or developing process monitoring schemes for clients. We do a lot of advanced data analytics, and I would say we are best known for our skills in process modeling. We have two softwares in that direction. One is our online monitoring control platform. We call Ops Control. We are currently testing the second generation, and you see a screenshot on the right hand side. We also work and started to internally use an offline data management and analytics software we call Data Control. It's also planned to have a release of that software later this year. Okay, so let's start with that webinar on sensors driving you mad. And you see it on the top right, That's a nice figure Alex made. So if you see that reality and your sensor measurements start to diverge, then very often your sanity goes down because it's just troubling. Yeah. So let's discuss a little bit about my personal criteria for sensor selection. So it's clearly not exhaustive, so I highlight a couple of things I thought important. So one of the things I always push for with clients is that I discuss robustness versus theoretical accuracy. So theoretical means manufacturers can only guarantee a certain accuracy under standardized, so typically lab conditions using clean water standards, right? And you should be clear on that is not what you will see in reality. Yeah. So then you look into things like measuring principles. Some principles are better suited for certain applications, locations, measuring ranges than others. Another focus is the availability of auto-cleaning features, auto-cleaning, auto-calibration, everything reducing the need for maintenance and calibration work, right? So that is very important. Any selection of sensors is location goal specific. So for example, if you need to measure with high accuracy in a low concentration range, that is probably limiting the selection quite a bit. We also go through all kinds of interferences with you in a structured manner, and that could include, for example, color, if you have a color sensitive measurement. One thing I always like to point out that it's not just the instrument as well, it's also the service you can get. So one statement I often make is pick a good and responsive technician, and that might actually be more important than having the perfect sensor. Yeah. So there's always a discussion of cost, right? And very often it starts with the price of the sensor, right? And I want to just make sure that you understand that this is really not the main cost of operating sensors. The main cost is actually maintenance and quality control, as you will be able to see on the next slide. Actually, my rule of thumb is still 1 to 2 hours per week per sensor, right? And do the math, that is quite some time going into your sensors. Another statement, understand the business model of the manufacturers. We all know that example with printers, right? So very cheap printers and quite expensive cartridges you have to buy to operate, right? So make sure you understand that and figure that out. So in this little example here, looking into the cost of ownership, that is a hypothetical example using an ion-selected electrode probe, and I have set the lifetime to 10 years, and what you can clearly see in light blue is that labor cost is about 70% in that specific case, right? So, and compared to the annual investment over the lifetime of 10%, it's clear that this is really a minor contribution. So what that means is focus on reduced maintenance and consumables so that in the end you drive down the real cost of ownership. Yeah, so that is one part. So that is the cost side. I also want to give an example on the benefits and then the cost-benefit analysis. In this example, I selected a plant using only DO control, and this is the cost to bring it to ammonia-based aeration control. Right? So I use a plant with about 100,000 people connected. I say introducing ammonia-based aeration control is about 15% savings, and the kilowatt hour is 10 cents. Right? So with that benchmark plan, that results in about $20,000 savings per year, and that is every year, right? So let's say you have to buy one ammonia probe and the annual cost I calculated or estimated is about $12,000, bringing the net saving down to about 8,600, down from 21,000. Right? So it's quite a hit on your saving potential. So let's assume you have 4 parallel trains and you want to play safe and you actually want to buy 4 probes, 1 probe in each train. The annual cost for sensor operation goes up quite a bit to 45,000, right? So and the net savings actually turn negative, right? So instead of saving money, you pay money. Yeah. So I'm not saying don't do that. I'm just saying do the math, do that analysis so that you know exactly what you are getting yourself into, right? On the other side, so this is direct cost savings. There's always a gain in knowledge, right? So as soon as you install an online sensor, there will be a gain, so you have a much better grip on the dynamics of the processes, and there will probably be other savings you can achieve. You can be more resilient. You may be able to detect problems earlier, so become more robust. So there are a lot of things to gain from online sensors, but clearly I want to recommend that you do a proper study, that you know what's happening. Yeah, so let's now move into sensor operation. Start with a couple of definitions. So on the left-hand side, offline, that means you take grab samples or you have an auto-sampler and you analyze that in the lab. Yeah? On the right-hand side, online instrumentation, you have ex situ instruments. This is typically a filtration unit in bypass or submerged, and then the permeate goes into the often wet chemistry analyzers. Yeah? So on the right-hand side, in situ probes, these are these sticks you put directly into the water. Yeah. In terms of quality control, for the lab, we have established standard operating procedures, right? So we have that in place, and if you follow these operating procedures, you get the quality you need. For the ex situ analyzers, they very often have auto-calibration routines, so that's relatively easy to do. But the standards are clean water standards, right? So any matrix effect would not be included, right? So I would still recommend that you do external quality control as well. Then you have the in situ sensors, and they need to be quality controlled. Yeah, so they are getting better as well. So you have a lot of self-diagnosis, but I still recommend to do and set up that external quality control. Okay, so a couple more definitions. So I like to split the different phases of the life cycle of a probe. And I start with commissioning. And what we include in commissioning is installation and something we call base calibration or initial calibration. So very important that you do that right in the beginning to make sure that when you move from that initialization phase into normal operation, that you know what the sensor is able to deliver and that there is no systematic error. Yeah? So then you go into normal operation, and then it's all about maintenance, right? And maintenance means you want to guarantee proper measurement conditions at all times. Something quite often overlooked is quality control. And what I mean by that is I want to be able to quantify the accuracy of a sensor over time. Right? So quantification means I need to see numbers to properly react instead of, oh yeah, that's not bad or good or bad. That's not something where you can adequately react to. So important is the quantification part. Okay, so a little bit into commissioning. Again, so I focus on some highlights here. That picture I like quite a bit. This is from Bob Dabkowski from HUG. He told me that you need a ladder to reach that sensor. So do you think that probe is properly maintained in quality control? No way. Yeah, so very important. That is part of the installation, that you make sure that it's easily accessible. Another nice setup of experiments here. So that is from Tracy Dewan from Mendelssohn Hauser. That is about probe mounting. Right? So that is a TSS probe in an aeration tank, and the first test installation here is straight down into the aeration tank. Sorry for the small numbers here. So that TSS probe measures around 4 grams per liter in terms of total suspended solids. Yeah. So what they did next is they slightly tilted the probe, and you see that suddenly the variation is heavily reduced, right? So the noise is less. And if you go to 90 degrees, it's even less, a little bit more. So what that means is that if the installation is wrong, you're actually measuring air bubbles. So for that TSS probe, an optical probe, the air bubbles are actually an interference, right? So they disturb the measurement process. So nice highlight of installation and the impact it can have. Another thing a lot of people will have seen, that's a DO probe, and you see these spikes, right? And what you see is it's quite regular, right? So that's what you want to look for, right? So check for regular patterns, and in this case it's actually cleaning, right? So the spikes means that you cleaned, so that's auto cleaning using pressurized air, and you switch back to normal operation too soon. So what you're measuring are these high concentrations due to the cleaning cycle. Yeah. So same you could have with calibration, with auto calibration, where you basically also measure the high standard instead of excluding that from the proper database. Yeah. So same principle. You go into the configuration menu and extend the time a little bit, the waiting time after cleaning or calibration. It might be that actually this is not a problem of the sensor, that is real, right? So you have these concentration spikes for whatever reason, and the sensor measures that correctly, right? And again, so you would try to find any schedule matching these spikes. Very often it has to do with pumping schedules. Yeah. So let's look a little bit more into calibration. So one of the first questions is, how do you calibrate your sensor, right? So do you do that with standards? But what about the matrix effect, right? So standard typically means clean water standard, right? So of course you can do a standard edition, but that is a lot of work to test. Yeah. You can also say, okay, so I want to compare that with reference measurements, so that was lab data. But then the question is that really representative? Is the lab method adequate, and so on? So if you want to work on that problem of being representative, you may go for a bucket experiment, we call that. This is basically for in situ sensors, where you put the probe into a well-mixed bucket and then you sample out of that bucket and analyze that in the lab. However, some of these in situ probes are quite sensitive to the in situ conditions, right? So it might not be a good idea because then they show different results. Unfortunately, you have to do that sensor by sensor and also location specific, right? So that is really something where you have to put that into a maintenance plan. Another problem, the difference between working range and measuring range. Measuring range is the range the instrument can cover, so where it can properly measure inside. The working range is only the range covered by the online sensor measurement. So in this case, that's a nitride sensor in situ probe, and the black triangles, this is actually the sensor measuring in normal operation. And you see that this is all around 0.2 milligram per liter. From a treatment perspective, that is actually a good number. 0.2 milligram per liter nitrite in the effluent is actually what you target. But that project was about nitrite accumulation, and we wanted to be sure that the instrument is properly measuring up to, let's say, 3 milligram per liter. Yeah? So what we did, we designed a specific experiment bucket test and spiked that bucket with high concentrated nitrite standard. So the point I want to make is that you have to design your data quality, right? So it's not something just coming. You have to make sure that you properly design for that. Good. So I mentioned that before. We strongly recommend to get things right from the beginning. So what we actually introduced is an initialization phase where we spend quite some time collecting enough data points to say, okay, that sensor is properly calibrated and properly works, right? So in this case, so on the x-axis you see the lab value, on the y-axis you see the sensor values, and then the green line is actually where you want all the measurements to be, right? In this case, all the blue dots are all over the place. And I have to admit, we never really figured out what caused that issue, right? It's clear that a new calibration wouldn't help, yeah? So, however, that information was sufficient for the plan to say, well, I think it's about time to buy new sensors. We did that, we checked them, highly accurate, we took them into operation, everything was fine. Same case here, but you see that all the blue dots are actually on the black line, and that is the new calibration curve we calculated in our monitoring and control platform. This is a screenshot from there. So it's clear that there is a bias of that measurement, and what we were able to do is to put that bias into the sensor. So we recalibrated the probe, and then everything was fine. For us, that means after that initialization, we move into normal operation. And this is another screenshot of our monitoring control platform where we basically track the performance in a control chart, and then on the right hand side you can see that that analyzer was properly calibrated. So you can get these instruments to work if you know what you're doing. Okay, so that brings us to maintenance, and specifically maintenance planning, right? So I want to start with the different types of maintenance. I know that's simplified. You can split that up even further. If we start on the left-hand side, reactive maintenance, this is basically something is broken, right? And you have to fix that. It's clear that the sensor is down, and you have to spend quite some time to get it back to work, right? So downtime of sensors, and it's quite tricky to get these things to work again. On the other side, it's proactive. Let's start with preventive maintenance. That's age-based or scheduled maintenance, and it states too early, but that is actually how you typically operate these sensors. The manufacturers have to recommend a certain schedule so that the sensor works at all times, right? So that is a classic scheduled maintenance. And then moving to the right, there's predictive maintenance, and that is condition-based. So that means you only do maintenance when you need it, right on time, right? So, but, well, how do you predict you need maintenance, right? So our solution actually is to drive predictive maintenance by quality control. So the role of quality control in our concepts is quite high. So let's start with the troublemakers with these instruments. So these are the filtration units. This is older units, but let's go through some experience. On the left-hand side, we destroyed that unit halfway through our measuring campaign. That was in the middle of winter, and actually we had a power outage, right? So we had heated tubes, but with a power outage, the little permeate tubes froze, and then the pump blocked, and we burned the pump. Yeah. So that was a prototype. They fixed a lot of things. They have more intelligence in there. They protect the pump, and then you can also put a battery package on that, or backup on that. So they improved that unit quite a bit. The one in the middle, that was our workhorse, serving multiple analyzers. However, so you have quite a big volume, right? And you have these big submerged pumps, and then depending on the pump rate, and we had quite a high pump rate, but still, due to the high volume, that unit added quite a bit to the response time of the analyzer, right? So in the first pump we used, we ended up with a response time of over 40 minutes for an ammonia analyzer. So be careful with that. Otherwise, quite a robust instrument. On the right-hand side, we destroyed that unit 10 minutes out of the box. Yeah, it was our fault. We scratched the membrane during installation, so we scratched that on the concrete. You can say too bad or too stupid, but yeah, I would also recommend to look into the design that it's actually better protected. The second point I want to make here, you can nicely see the yellow color. That means, so that plant is heavily dosing iron for chemical phosphorus removal, and we had to replace all the membranes at least once a year. So no chemical cleaning would help there, right? So keep that in mind as well. You have to replace them if you do dosing. Okay, so let's look into analyzers. So these are all new instrument, new generation, lots of improvement, less chemicals, less maintenance, a lot of diagnosis capabilities, so self-diagnosis. I think for me the main change is in the pump, right? So before everyone was using these peristaltic pumps, and then you had to move the tubes back and forth all the time and replace them and so on. Now most of or all of them use piston pumps, so less maintenance required, and that brings down the maintenance work quite a bit. Also with the filtration units, new materials, less maintenance, all of them said they can actually measure or filter in raw wastewater. I didn't test that myself, but happy to be convinced. There's a lot going on, and really look into that as well. And then we have the famous in situ sensors everyone is talking about. Very important is auto cleaning, specifically for the optical probes. There are wipers, air, water, ultrasonic cleaning. My preference clearly is air, most aggressive, so best cleaning results, but I also like the combination of air and ultrasonic because you remove different clogging out of the spectra. Don't forget manual cleaning, and manual cleaning means, at least for the optical probes, cleaning with a brush and then chemical cleaning according to manufacturer specifications. Do that one step after another. Very easy check. Check the signal before and after cleaning. If there's a jump in the signal, you know exactly that there's something accumulating on your measuring. Yeah, very, very important, very easy to check. Quality control, again, so you need to externally organize quality control. That is essential. So that brings us to quality control. If I discuss with clients, and I typically like to start with a workshop, one of my first questions is, what is an acceptable measurement for you? Right? And then there's typically a bit of silence and some ideas. My questions actually are, what accuracy can the sensor deliver? Right? And so I want to have that quantified. I want to have clear numbers. The next question is, what is required for your control or monitoring system? Right? So you see that these are two sides of the story, and actually most of our work is to moderate discussions, to close the gap between the two sides. What makes it tricky is that typically there are two groups involved, right? So you have the instrumentation staff, and then you have the process operators and engineers, and they have to communicate and get together, right? And that is, at times, that's quite a tricky bit. Very important actually is to be able to properly quantify both sides, because only then you can come to a conclusion or a solution. Last question is, how fast do you need a measurement, right? So that is the response time, and that is important for control system design and tuning, right? So very important information for your control people to know how long it takes to get the measurement, right? So that may change the tuning completely or make it impossible to get that control system to work. Little bit of theory here on systematic and random errors. So let's assume the green dashed line, that is the true value, right? So let's assume that is one sample and you measure that one sample 10 times, right? And you see that the measurements, the black dots, are not all on the green line. They are actually varying around the green line, right? So if you have a normal distribution, the average without outliers is actually the true value then. But that noise around that green line, that's what we call a random measuring error, or in technical terms, precision. Yeah? However, in fact, the red line is the true value, right? And then the difference between the red and the green line, that is a systematic error, and we call that trueness. Yeah? Very important. We want to prevent systematic measuring errors, and we want to quantify random errors. Random errors, you can work on that by changing, for example, installation, as we saw, but very often that is linked to the measuring principle. So you will never get completely rid of the random error. So you have to be aware of that. That's also very important to set up your maintenance plan, because what you want is you want to trigger recalibration if there's a systematic measuring errors. What you don't want to do, really clearly don't want to do, is you trigger recalibration based on random errors. You follow the random error, and that is just asking for trouble. Yeah. Very important as well, plot everything. The human brain is very good to detect anomalies in plotted data, not so good to detect that in spreadsheets, right? So really plot everything. So what you see here in that example, the client called us in a very noisy signal. That was an ion selective electrode probe, and we analyzed and then changed the reference electrode, and then you see quite a smooth signal resulting or after repair. So that means after repair, that smooth signal, that is the normal condition. And if you suddenly see that noisy signal, then it's clear that there's something not quite right. Yeah, and of course, we also put that into our automated fault detection package, so that this is automatically detected. But again, so just looking at it helps a lot. Also find the right plot type. So for our reference measurements, we plot that in a Shewhart control chart. what that is we are plotting the difference between the sensor and the lab value over time. Very good to detect any drifts, outliers, shifts, jumps, whatever. Yeah. However, what you don't get out of that chart is information on the measuring range. So if you have a wrong calibration, you would not easily be able to detect that. So that's why we have the calibration chart as well, and that gives us a very good indication of the calibration. Okay. So let's stick a little bit longer to that reference sampling. The first question really to ask is, when do you collect the sample, right? So that means next to the probe. Don't do that every morning at 8, right? Because then you will just have a little tiny cloud of data. What you want is you want to cover most of your measuring range. If you cannot do that because the working range is too small, you have to design special experiments. For example, a bucket test where you spike high concentrated standard, right? Very important design for that. The second one, little tip, so when we analyze sampling procedures, what we very often find is secondary sampling errors. That means you sample into a larger bottle, you take that bottle to the lab, and then you don't properly mix, right? And then you subsample from that larger bottle for your analysis, and you don't get the same sample in your subsampling. Yeah. I also like to filter directly after sampling. I use these syringe filters for that. And then of course you want to get the sample to the lab as soon as possible. So in the lab, just follow the standard operating procedures. So they are established, and if you follow them, you get things to work. One little tip, check your micropipettes, right? So the micropipettes are really the main source of errors in your lab work. Very easy to check. You can do that by just pipetting into a little beaker on a lab scale, right? So very easy to check, but micropipettes are really the main source of error. We can also guide you through a complete analysis of your lab analytics, but that is a little bit too much for today. Okay, so you collected all the lab, the reference measurements, but you need to get online data from your SCADA historian or DCS together with the lab data, maybe stored in your lab information management system. And funny enough, that is typically not that straightforward. Very important, you need to get that together to be able to analyze, and also in the end, of course, you want to be able to visualize any recommendations, right? So as mentioned before, what we like to do is we use the data quality control to drive maintenance, right? And that's how we do that. That's another screenshot of our monitoring control platform, where we actually have a schedule set up for the instrumentation people. And again, highlighting you can get this stuff to work if you know what you're doing. Another, that's a repetition, I know. If you set up your recalibration criteria, use control charts, right? So the control charts are set up so that you detect systematic errors. Don't do percent error per individual sample. So that just gets you into trouble because you follow the random noise. Okay, so this is the reference measurement. So let's say you do that once a week. So that's a typical recommendation. But if you're running a control or monitoring scheme, then you actually want to check every single value entering these systems, right? So how do we do that, right? So of course you cannot measure every second in the lab, right? So that would be a bit too much. So what we do is we develop methods to provide high quality and high resolution data We are using multivariate models for that. We use that for fault detection. One of the critical points is actually to differentiate sensor and process faults. Right? So sensor faults mean that you don't want to have that entering your system. You want to exclude that, replace that maybe. And then you have process faults, and that's actually what you're interested in. Right? So you need to know if there's something wrong, so you cannot exclude process faults. So the tricky bit is how do you differentiate that? And we do that by using multivariate models, and that's highly simplified, of course. But in this case, that's on the right-hand side, that turning figure. You see that all the blue dots, that's an ellipse, and they're all in one plane. And if an individual measurement moves to the outside of that ellipse, that means that the process is changing. Whereas if an individual measurement sticks out of that plane, that is a very good indication that something might be wrong with the sensor. Yeah? Good. That brings me to the take-home message. In terms of sensor selection, that is really location specific. Make sure you figured it out for very low temperatures, so freezing tubes, for example, that you cover that one. Also very high concentration could mean that you cannot measure under standard conditions anymore because it's too hot, right? So that's the other extreme. In terms of cost, really calculate the annual sensor cost. Do that exercise. It will help you a lot to better understand the cost structure and the cost of ownership of your sensors. InCTRL is offering expert advice, and we can support you in that. Commissioning. So proper installation, I think I showed that, is key. What we highly recommend is that initialization phase where you make sure that the sensor is properly working right in the beginning, and only after you pass that step you go into normal operation. Really, that keeps you sane instead of tweaking. Training of your operators is also very important. We offer that as training courses. We do a lot of hands-on and classroom settings, and we also can support you in calibration of your probes, that base calibration or initialization. Yeah? And we also have the software in place to support that. In terms of maintenance, this is really the essential part for operation, but also the main cost factor. So you want to basically get to that compromise, that sweet spot where you limit the effort you spend on the sensor and maximize the quality of the sensors at the same time. That, in my opinion, is only possible if you have a maintenance plan in place. What we do is we drive that by quality control, so that's a special concept we have developed. InCTRL can help you in developing your own maintenance plan, or we can also provide this in form of software. Quality control statement here is plan your data quality, right? So if you understand what to do, the quality is increasing. You need to be able to quantify your accuracy. Yeah? We still recommend regular reference measurements, but we complement that by our online data quality control tools. And we also package all that in customized software solutions. So that's that's my part of the presentation, and I hand that back to Alex. Thanks.
Well, Leiv, thank you very much. For those of you who missed our last webinar as part of our series, the Make Your Aeration System Work, presented by Oliver Schra at InCTRL Solutions, that webinar is available on the InCTRL YouTube channel. You should be able to find it, but if you're having any trouble, feel free to drop any one of us an email, and we'd be happy to send you the link. And we've got a couple of upcoming webinars. On Wednesday, July 8th, I'll be presenting the What Did I Just Feed My Digester webinar, a guide to predictive modeling of multi-feed biogas plants. And 2 weeks after that, on July 22nd, our colleague Ivan Miletic will be presenting Garbage In, Knowledge Out, application of advanced data analytics for water resource recovery facilities.